Welcome back to Mechanical Engineering Made Simple. Today, we are undertaking quite a critical mission. We're doing a rapid, high-impact deep dive, focusing on the absolute foundational concepts, the essential mathematical toolkit, really, that underpins thermal and fluid sciences. We're aiming to extract those, foundational nuggets you need to understand exactly how heat moves and how fluids flow.
Yeah, this is absolutely fundamental territory. We're pulling together four powerful areas from the source materials you've gathered. We'll cover the four thermal transport modes, the core conservation equations, mass and momentum, and then look at how engineers actually grapple with material properties.
With thermophysical properties.
Exactly. And finally, the incredible power of dimensional analysis, which lets us scale things up or down.
Right, taking insights from the lab bench to, say, a massive industrial process. Our goal here is pure leverage, isn't it? We want to quickly unpack these concepts, which can often seem dense.
Very dense sometimes.
Give you the context, the vocabulary, maybe those aha moments that make the real difference.
Going beyond just knowing the equations to actually understanding the mechanics.
Exactly. Okay, let's unpack this first part then. When we look at how thermal energy actually moves around, the sources identify four basic modes: conduction, convection, phase change, and radiation. Let's start with maybe the most intuitive one for solids or stationary fluids: conduction.
Right, conduction. That's essentially heat diffusion. It's typically described by Fourier's law. But what's fascinating, and engineers do this almost immediately, is they translate this physical process into an electrical analogy.
Using thermal resistance, RCD.
Precisely. RCD is defined as the length the heat travels divided by the thermal conductivity, K, times the cross-sectional area, A, so L over Ka. And it really mirrors Ohm's law for electrical current. It lets you visualize complex thermal paths, almost like simple electrical circuits.
Okay, and that analogy gets really interesting, doesn't it? When we move beyond just simple walls. Like, consider one-dimensional conduction with internal heat generation. Think energy dissipation inside a chip, or maybe a battery cell.
Yeah, that's a great example. If that heat generation is distributed uniformly through the whole volume, like, say, evenly along the length of a current-carrying wire, well, the sources reveal something critical for design here.
Which is?
The overall thermal resistance in that distributed case is only 1/4, just 25% of the resistance you'd get if the same total amount of heat was generated only right at the very center.
Wow, 1/4. That's a huge difference.
It is. And that 4x factor fundamentally changes how you approach thermal management.
Because if you centralize the heat source, the peak temperature inside could spike,
Right.
potentially causing failure.
Exactly. By distributing the heat generation, you keep those potentially dangerous temperature peaks much, much lower.
Which explains why, battery designers and chip engineers work so hard to spread that thermal load out.
Precisely. And speaking of design realities, we can't always assume perfect materials or perfect contact. When two real solids touch, even if they look smooth, we get this thing called interface contact resistance, ARCO.
Okay, so there's a measurable temperature drop right at that joint. Why does that happen if the surfaces look smooth to the eye?
It gets down to the microscopic level. Real surfaces aren't perfectly flat. They have tiny peaks and valleys called asperities, roughness and slope, essentially.
Oh, okay.
These asperities mean the actual solid-to-solid contact might only be, say, 1%, maybe even less, of the apparent area you see.
So the heat has to struggle to get across.
It does. It has to transfer mainly by conduction through those tiny solid contact points, but also, crucially, through the fluid, usually air trapped in all the microscopic gaps between them.
Right, so that's why we use thermal interface materials, like thermal paste on a computer processor.
Exactly.
It's not just filling visible gaps, it's replacing that poorly conducting air in the microscopic gaps with something much more conductive. It helps bridge those asperities.
You got it. It drastically drops that ARCO value.
That makes perfect sense. Okay, shifting gears now. What about moving fluids? That brings us to convective heat transfer.
Right. Convection is where the bulk motion of the fluid itself becomes a major player in transporting heat. We quantify this using the heat transfer coefficient, little h, and that allows us to define a convective thermal resistance, RCV, very simply.
Oh, simple.
Just 1 over h times s. So 1 divided by the product of the heat transfer coefficient and the surface area the fluid touches.
Okay. And can we use these resistance ideas for processes that change over time, like heating something up or cooling it down? Tell us about the lumped capacity model.
Yes, the lumped capacity model. It's a really useful simplification for analyzing transient heating or cooling. But it only really works well when the internal resistance of the object Its resistance to heat flow within itself is negligible compared to the external resistance, like the convection off its surface.
So give us an example.
Think of it this way. Drop a very small, thin metal needle into cold water. It cools down almost instantly, right? The temperature inside is pretty much uniform throughout the process.
Yeah, makes sense.
Now drop a big, thick steak into that same water. The outside cools quickly, but the center takes ages to cool down. The temperature is definitely not uniform.
Right, big difference.
The lumped capacity model is perfect for the needle. High internal conductivity, small dimensions.
Yeah.
Not so good for the steak. For those cases where it applies, the system's time behavior, how fast it heats or cools, is just defined by its thermal time constant.
And that is?
Simply the product of the total external resistance, R, like that convective resistance we mentioned, and the object's thermal capacitance, which is its mass times its specific heat, mc. So R times mc.
Okay, so all this talk about conduction, convection, resistance, it all fundamentally depends on the materials involved, doesn't it?
Absolutely.
On their thermophysical properties, as the sources call them. These are the raw data that fuel all our engineering calculations. And the sources seem to divide them into two critical camps.
Yes. That's a very helpful distinction. First, you have the thermodynamic properties, sometimes called equilibrium properties. These include things like temperature, pressure, density, enthalpy, and specific heat capacity, ZP or CV. They describe the state of a system when it's stable, at equilibrium.
Okay, state properties.
Right. The second camp is transport properties, or non-equilibrium properties. These describe the material's ability to move stuff, mass, momentum, or energy when things are not in equilibrium. So this includes thermal conductivity, lambda, viscosity, eta, and thermal diffusivity, alpha.
And here's a point that jumped out at me from the sources, something maybe easy to overlook. The thermodynamic properties are generally considered much more accurate, much better defined by measurement, for common fluids at least, than the transport properties are. Is that right?
That's absolutely critical. And you have to ask why.
Okay, why?
Well, think about measuring pressure or density. It's relatively static, right? You measure the steak. But measuring viscosity or thermal conductivity, you actually have to induce a gradient. You need flow to measure viscosity or a temperature difference to measure conductivity.
Ah, you're observing a dynamic response.
Exactly. And those dynamic measurements are just much more susceptible to experimental errors, to disturbances in the environment. It's inherently trickier.
So the engineer constantly has to be asking, given this uncertainty in my input properties, how accurate does my final result really need to be?
That's the perpetual challenge. How much accuracy is enough?
Now, to deal with this, especially for fluids, modern analysis relies heavily on something called an equation of state, often based on Helmholtz energy.
Yes, the Helmholtz energy formulation is incredibly powerful. It's typically composed of an ideal gas part and a residual part that accounts for real fluid behavior. So a 0 plus O residual.
And what's the big advantage, the leverage, of using this approach?
The leverage is mathematical consistency and efficiency. If you have this one master equation for Helmholtz energy as a function of temperature and density, you can then calculate all the other thermodynamic properties, pressure, entropy, specific heat, everything, just by taking its partial derivatives.
Wow, okay.
Instead of needing separate, potentially inconsistent curve fits for every single property, this one function generates them all. It's the mathematical bedrock.
And to make this practical, engineers turn to tools like the NIST databases, right? They implement these high-accuracy algorithms.
Exactly. Databases like ReefProp from NIST are indispensable. But what about when you're dealing with a new fluid, something not in the database?
Good question. What then?
That's where predictive methods come in. And a very important one mentioned is the method of extended corresponding states, or ECS.
Extended corresponding states, how does that work?
It's basically a clever scaling technique. It uses the well-documented properties of a known reference fluid and scales them based on the critical temperature and critical density of your unknown fluid.
So you can estimate the behavior of, say, a new refrigerant without having to do all the experiments from scratch.
Precisely. It allows for quite accurate predictions, saving a lot of time and effort. It's widely used in chemical and process engineering.
Okay, let's switch focus now to solids. How does heat move through them?
In solids, thermal transport is mainly down to two things. In metals, it's largely the movement of free electrons.
Yeah.
similar to electrical conduction. But in all solids, including insulators, it relies on molecular vibrations.
Vibrations, like atoms jiggling in the lattice.
Exactly. And these vibrations are quantized, meaning they come in discrete energy packets. We call these packets phonons.
So phonons.
So you can think of a phonon as a sort of particle of vibrational energy moving through the crystal lattice. That's how heat actually propagates through an electrical insulator.
And the differences in thermal conductivity that result from these mechanisms, they're staggering.
Absolutely huge ranges.
The sources mention metals like silver way up at, 427 watts per meter Kelvin?
Yeah, very conductive.
While dielectrics, insulators like paper, can be down around 0.12 Willer-MK.
A massive difference.
And then you have the famous outlier, diamond, up at 2310 Willer-MK.
Diamond is just incredible. It's because its crystal structure is almost perfect. Very light atoms, very strong bonds, very stiff lattice.
So the phonons can travel easily?
Almost unimpeded. There's very little scattering. Now, unlike fluids, where pressure is a big factor, a solid's properties are mostly independent of pressure. But, and this is key, their thermal conductivity can be extremely sensitive to things like impurities or defects in the crystalline structure, especially at low temperatures.
So even tiny flaws can disrupt those phonon pathways.
Dramatically. Even parts per million impurities can sometimes slash the conductivity. It makes measuring and predicting solid properties quite challenging.
How do we measure them accurately then?
We use specialized techniques. Things like differential scanning calorimetry or DSC are common for measuring specific heat. And for thermal diffusivity, the flash method is a widely used modern technique.
Okay, moving towards the flow aspect now. The ultimate language here is mathematics, isn't it?
It really is.
We have these two core conservation laws that universally define fluid flow. The first one is the continuity equation. What does that represent?
Fundamentally, it represents the conservation of mass. Keep track of the mass.
Simple idea, but the equation can look complicated.
In its most general vector form, yes, it accounts for unsteady three-dimensional flow where density can change. But the core idea is simple. The rate at which mass builds up inside a specific volume over time must be exactly balanced by the net rate at which mass flows across the boundary of that volume. Mass in minus mass out equals accumulation.
Okay, that makes sense. And if the fluid is incompressible, meaning its density is constant, like water in many situations?
Then it simplifies significantly.
Yeah.
The time-dependent term drops out, and the equation basically says that the volume flow rate in must equal the volume flow rate out of any given region. What goes in must come out.
Got it. What's the second core law?
That would be the momentum theorem. This comes straight from Newton's second law. Force equals the rate of change in momentum, F dmv dt. When we apply this principle carefully to a fluid moving through a control volume, considering all the forces acting on it, pressure forces, viscous forces from internal friction, body forces like gravity, and we relate those forces to the change in the fluid's momentum as it passes through, we eventually arrive, under certain assumptions, at the Navier-Stokes equations.
Ah, the famous Navier-Stokes equations, the governing equations for what conditions specifically?
Typically, for incompressible laminar flow with constant viscosity, they essentially balance all the forces acting on a fluid element against its inertia, its change in momentum.
Okay, so if these equations are the definitive statement on how these fluids flow, why don't we just, solve them for every engineering problem?
If only it were that simple.
What's the catch?
The catch is they are notoriously difficult to solve. They're nonlinear partial differential equations, meaning we often can't find exact analytical solutions, especially when the flow becomes turbulent, which very often does in engineering applications.
So even with powerful computers running CFD, computational fluid dynamics, it's still hard.
It's still computationally very expensive and requires careful setup and interpretation. The difficulty in solving Navier-Stokes directly is precisely why engineers rely so heavily on another powerful tool.
Which is?
Dimensional analysis.
Right. When you're faced with a complex problem, maybe flow in a pipe, heat transfer from a fin involving, say, 8 or 10 different variables, velocity, diameter, density, viscosity, pressure drop, roughness, specific heat, it gets overwhelming fast.
Exactly. Trying to experimentally determine how pressure drop changes when you vary each of those things independently would be a nightmare.
So dimensional analysis helps cut through that complexity using the Buckingham theorem.
Yes. Buckingham is, honestly, an incredibly elegant piece of mathematical leverage. It provides a systematic way to group all those initial, potentially numerous physical variables into a much smaller, more manageable set of dimensionless groups. We call them pi terms.
How does it know how many groups?
The theorem tells you the number of independent dimensionless groups you need is equal to the number of original variables minus the number of fundamental dimensions involved, like mass, length, time, maybe temperature.
Let's use the classic example from the sources, predicting friction loss or pressure drop in fluid flow through a pipe.
Perfect example. You might start with, say, 6 variables, the pressure loss per unit length, the fluid velocity, the pipe diameter, the pipe roughness, the fluid density, and the fluid viscosity.
6 variables.
And the fundamental dimensions involved are mass, length, and time. So 3 dimensions.
6 variables minus 3 dimensions.
Means you only need 6 3 equals 3 independent dimensionless groups to describe the entire phenomena.
And those groups are?
Typically, they turn out to be the friction factor, F, which represents the dimensionless pressure drop, the relative roughness, id, comparing the roughness height to the diameter, and the reciprocal of the Reynolds number, which involves velocity, diameter, density, and viscosity.
So instead of needing complex multi-dimensional plots relating pressure drop to velocity and E diameter and density and E viscosity and E to roughness,
You just need one chart, like the Moody chart, which plots the friction factor, F, against the Reynolds number, with different curves for different relative roughness values.
that's the power. One set of experiments on one pipe with one fluid can suddenly be used to predict friction loss in a completely different pipe with a different fluid at a different velocity, as long as the dimensionless group's Reynolds number and relative roughness are in the right range.
Exactly. It allows for scaling and generalization of experimental data.
And this is fundamentally why dimensionless numbers like the Nusselt number for convection, the Prandtl number relating momentum and thermal diffusivity, and the Reynolds number for flow regime are the absolute lingua franca of transport phenomena in engineering.
They logically group the interacting variables, simplify complex behavior, and provide the essential framework for correlating experimental data and applying it broadly. They connect the fundamental physics to practical engineering charts and correlations. #tag outro.
So we've covered quite a bit of ground today. We navigated the 4 modes of heat transfer, conduction, convection, phase change, radiation, dug into the critical thermophysical properties of fluids and solids.
Including that fascinating world of phonons and the power of the Helmholtz energy approach.
Right. And we touched on the core conservation equations governing flow and the immense practical leverage we get from dimensional analysis.
It really highlights how interconnected these concepts are, but it also raises, I think, an important question for you, the practicing engineer or the student, to consider.
Oh, what's that?
Well, we rely so heavily on these elegant mathematical models, like Navier-Stokes, and these powerful predictive concepts, like extended corresponding states. But as we discussed, these models are entirely dependent on the accuracy of the underlying thermophysical property data we feed into them: viscosity, thermal conductivity, density, specific heat, and so on.
And we know measuring those, especially transport properties, can be tricky, and materials, especially solids, vary due to impurities.
Exactly. So the question is, considering these inherent uncertainties in the data, how much accuracy is really enough for practical engineering design? When does the quest for more precise property data yield diminishing returns compared to, say, refining the model itself, or simply using appropriate safety factors?
That's a really interesting point. How does that continuous refinement of property data fundamentally change our designs versus refining the models or just accepting uncertainty?
It's a constant balancing act in engineering. Definitely something to chew on.
Indeed. Lots to think about there. Until the next equation, I'll see you in the flow.